students, so this question is about two spherical shells. So these are two spherical shells of different radius. It doesn't say what is the charge on them. So let's say the charge here is Q1 and Q2, the radius is R1 and R2. Now we connect them with a wire, okay, and equilibrium is attained. What does it mean? They attain the common potential. Why? Because charge from one transfers to the other. So let's say after you connect it, the new charge on this is this, it loses minus Q, and the Q2 one gains Q. Now they are at the common potential. So the potential on the first one is given by K, the charge on it, K Q1 minus Q divided by the radius, and the charge on the second sphere is K, which is now the total charge is Q2 plus Q divided by R2. So this has lost a charge Q, this has gained a charge Q. After some time, this exercise of movement of charges, they attain equipotential. So now the potential has become equal. No further movement of charge is possible. This is the way you need to interpret it. So let's equate these two. So K Q1 minus Q upon R1 is equal to K Q2 plus Q upon R2. Okay. So Q1 R2 minus Q R2 is equal to Q2 R1 plus Q R1. Okay, now what we do is Q1 R2 minus Q2 R1 is equal to Q R1 plus R2, and Q is equal to Q1 R2 minus Q2 R1 upon R1 plus R2, right? So now you have the charge which has flown from this to this. So let's calculate the new charges, okay? So Q1 minus Q1 R2 minus Q2 R1 upon R1 plus R2. Okay, let's calculate Q1 R1 plus Q1 R2 minus Q1 R2 plus Q2 R1 divided by R1 plus R2. So let's see if something gets cancelled. Q1 R2, I think this goes away. So you are left with Q1 plus Q2, and this is R1 plus R2. If I take R1 common, if I take R1 common from these two, right? So I will be left with R1. Okay, so R1, and I will just write it as R1, okay, divided by R1 plus R2. So this is the charge on the first shell after the equilibrium is attained. Let's calculate the charge on the other one, which is this. So we will add. So Q2 plus the charge which has moved. This is the charge which moved. Q2 plus Q1 R2 minus Q2 R1 upon R1 plus R2. So this is equal to Q2 R1 plus Q2 R2 plus Q1 R2 minus Q2 R1 divided by R1 plus R2. So let's say what gets cancelled. So I think this cancels, and we can take R2 common out of it. So R2 Q1 plus Q2 divided by R1 plus R2. Quite symmetrical, right? So this is a new charge on this particular shell, and this is the new charge on the second shell, right? Let's go. So now we have, so far what we have done is we have only established what charge should move for equipotential. That we have established, right? Now let's talk about another situation. So it says finally you have to find the ratio of the magnitude of the electric field on the surfaces of the sphere. But there is a mention. If you if you consider the magnetic field on the surface of the first one, right? First shell, which is this. The electric field here is because of the shell itself. R1 has a charge on it, which is this. We know if there is a charge on a spherical shell, E is equal to kq by r square. But there is another shell which is there. It also produces an electric field, but it says the distance is so large. It says as compared to the radius, right? The distance of separation between the two is very large, which means it's an infinite distance. So the electric field which is produced by R2 on R1 is 0. And similarly, the electric field which is produced by R1 on the surface of R2 is 0. So the only electric field we have to consider on the surface is because of the charge on the shell itself. Otherwise, normally if these were very close to each other, you would calculate one electric field due to this, then the second electric field will be due to this, and you will do a resultant. And similarly here, it has its own electric field and the electric field coming from the second one. But this is not the case. It says they are at very large distances. When the distance is very large, and we know E is inversely proportional to R square, if R is very large, electric field becomes 0. So electric field due to 1 on 2 is 0, and electric field of 2 on 1 is 0. So we just need to worry about electric fields of the individual shells on their surfaces. Alright, now what do? Let's now work out the electric fields. So the electric field of the first one on itself, on the surface, right? E1 electric field of this one will be written by K. What is the charge on it? KQ, right? So Q1 plus Q2 R1 divided by R1 plus R2. This is the charge. And what is its own radius? R1 square. So I have applied the normal formula. On a spherical shell, the electric field is this. Inside the hollow spherical shell, there is no electric field here, okay? On the surface, it is this. Now let's write the electric field of the second one. So K, I am writing this charge, right, which we have just arrived at, sorry, this total charge. So K, Q1 plus Q2 R2 divided by R1 plus R2. This is the expression of the charge, K times charge divided by its radius square, right? So we have been able to establish the electric field. What are we supposed to find? Electric field of E1 by E1 by E2, because we have to compare radius 1 with radius 2. So I will write this in the numerator. This expression is in the numerator and this expression is in the denominator. You can see if I do that, K will get cancelled, right? Q1 plus Q2 will get cancelled. R1 plus R2 will get cancelled, and you will be left with, and you can see there is an R1 and an R2. So this will become R1 and this will become R2. So finally, you will only be left with 1 upon R1 divided by 1 upon R2. So this will become R2 by R1. So the ratio of electric field on the surface of the first shell of radius R1 to the second one is given by R2 by R1. Let's look at the choices, right? So this choice is correct. This choice is the correct one, right? So lengthy problem, but if you keep patience, you can solve this easily, right? You should have known the concept of equilibrium. If two shells are in equilibrium connected by a wire, their potential is common. To start with, the charges are separate. When you connect them with a wire, the charges start flowing between them. Whatever is the loss of this is a gain of the other, and then they attain equipotential. No further movement of charge. But we should, at the first step, using this logic, calculate the charge which moved. and we've actually found out the charge that moved. Then we changed the charges on the shells like this, and then we use the expression of electric field. So you have to know a lot of things. The fact that at infinite distance the electric field will not exist. So this particular shell has no electric field here, and similarly this shell has no electric field because the inverse ratio, right? Distances r tends to infinity, E becomes 0 at very large distances. So I hope you enjoyed the explanation. Please go through my playlist of electrostatics. I have a playlist of Gauss, electrostatic potential, and around 300 problems and concepts explained in these videos. You really don't need to join anywhere. Just refer to NCERT or some book and you will be able to solve most of the questions using this explanation that has been given on this channel. So I look forward to see you soon with my next numerical. Till then, goodbye.